Solution of a differential equation. An ordinary differential equation of the nth order is an equality that relates the independent variable to the nth derivative and lower order derivative as well. Some examples are t squared times the second derivative of x with respect to t plus t times the first derivative of x with respect to t plus x equals t squared. This is a second order differential equation where t is the independent variable and x is the dependent variable. Square root of 1 minus the second derivative of y with respect to x equals to y is a second order differential equation where x is independent and y is dependent. Hence, a general form for an nth order differential equation with x independent, y dependent can be expressed as a function f of x, y, the first derivative of y with respect to x, up to the nth derivative of y with respect to x equals to 0. Equation number 1. Where f represents a function depending on x, y and the derivatives of the dependent variable y up to order n. It will be assumed here that the differential equation holds for all values of x in the open interval I, that is x lying between a and b, where a or b could be infinite. In majority of the cases, the highest order term, the nth derivative of y with respect to x, is usually isolated and written in the form the nth derivative of y with respect to x is equals to function of x, y, the first derivative of y with respect to x up to the n-1th derivative of y with respect to x. Equation number 2. Explicit solution. Definition. If a function g of x satisfies equation 1 or 2 for all x in the interval I when substituted for y in the equation, then it will be referred to as the explicit solution to the equation on I. For example, solutions written in form of the dependent variable are termed as explicit solution. Y equals e raised to the power of m times x, y equals to ax plus b over x, or y equals to a sine of alpha x plus b cosine of alpha x. Problem number 1. Show that the function phi of t equals t squared minus 1 over t is an explicit solution to the second order differential equation, second derivative of x with respect to t minus 2x divided by t squared equals to 0, but phi of t equals t cubed is not. The functions phi of t equals t squared minus 1 over t, then we take the derivative of phi with respect to t, gives us 2t plus 1 over t squared, and the second derivative of phi of t with respect to t is 2 minus 2 over t cubed, are defined for all values of x except at 0. Now substitute these values into the differential equation. The second derivative of phi minus 2 over t squared times phi of t equals to 0, we get 2 minus 2 over t cubed minus 2 over t squared times t squared minus 1 over t equals to 0. When we simplify, we get 2 minus 2 over t cubed minus 2 plus 2 over t cubed equals to 0. All the terms get cancelled out, leaving us with 0, which is equals to 0. Because this is valid for any x not equals to 0, the function phi of t equals to t squared minus 1 over t is an explicit solution to the given differential equation on the interval negative infinity to 0, union 0 to infinity. Now, for the function phi of t equals t cubed, we have phi prime of t, that is the first derivative of the function phi with respect to t is equals to 3t squared, and the second derivative will be 6t, such that phi double prime t minus 2t squared phi of t, which is the differential equation, now becomes 6t minus 2 over t squared times t cubed, which gives us 6t minus 2t. On subtraction, we get 4t, which is valid only at the point x equals to 0 and not on any interval. Therefore, phi of t is not a solution. Show that for any choice of the constants alpha and beta, the function f of x equals to alpha times e raised to the power of x plus beta times e raised to the power of negative 2x is an explicit solution to the linear equation second derivative of y plus the first derivative of y minus 2 times y equals to 0. The functions f of x equals to alpha e raised to the power of x plus beta times e raised to the power of negative 2x. Then the first derivative of f with respect to x equals alpha times e raised to the power of x minus 2 beta times e raised to the power of negative 2x, and the second derivative of function f equals alpha e raised to the power of x plus 4 times beta times e raised to the power of negative 2x are defined for all x. Substitute the second derivative of the function f, the first derivative of the function, and the function itself into y double prime plus y prime minus 2y to get alpha times e raised to the power of x plus 4 beta times e raised to the power of negative 2x plus alpha times e raised to the power of x minus 2 beta times e raised to the power of negative 2x minus 2 times alpha e raised to the power of x plus beta e raised to the power of negative 2x. On performing the required algebra, we get this value is equals to 0, which satisfies the differential equation. Hence, f of x is an explicit solution to the given differential equation on the interval negative infinity to infinity for any choice of the constants alpha and beta. Implicit solution. Definition. A relation h of x and y equals to 0 will be an implicit solution to the equation f of x, y, derivative of y with respect to x, up to the nth derivative of y with respect to x on the interval I if it defines one or more explicit solution on I. For example, solutions of the form x plus y plus e raised to the power of xy equals to 0 are explicit solutions. Problem number 3. Show that x squared plus t minus 3 equals to 0 is an implicit solution to the derivative of x with respect to t equals negative 1 over 2x on the interval negative infinity up to 3. We have x squared plus t minus 3 equals to 0. Equation number 1. Here the dependent variable x is not expressed in terms of the independent variable t. So we say that 1 is expressed in the implicit form. Using the technique of implicit differentiation, we differentiate 1 with respect to t to get 2x times derivative of x with respect to t plus 1 minus 0 equals to 0, isolating derivative of x with respect to t, and that gives us negative 1 over 2x. Equation number 2. Now we can express equation number 1 explicitly as x squared plus t minus 3 equals to 0, or x squared is equals to 3 minus t. Solving for x, we get plus or minus square root of 3 minus t, which can be also expressed as phi of t is equals to plus or minus square root of 3 minus t, which is defined for all t values less than 3, that is, t belongs to the interval negative infinity to 3. Hence, x squared plus t minus 3 equals to 0 is an implicit solution to the differential equation derivative of x with respect to t equals negative 1 over 2x on the interval negative infinity to 3.